Okay, we are continuing on in honors chemistry. Today we're doing periodic trends. Hopefully you have printed off a periodic table with arrows on it, and let's go ahead and write in the trend that we talked about at the end of the last video. So we were talking about metallic characteristics, and so on the first arrow going down, please write metallic characteristics increase. Okay, so that simply means that sodium is more metallic than lithium, and a lot of that has to do with the electrons as you go down this family or group, or any of these families or groups, are further from the nucleus, and so they're more easily removed. If a trend does one thing going down, the family or group is going to do the opposite going across, and so on the first arrow going across, simply write metallic characteristics decrease. Okay, atomic radius. So atoms do not have clearly defined outer limits. They have an electron cloud. Their size has to be measured indirectly. So there's a picture in your book in this chapter. For metals such as sodium, atomic radius is defined as half the distance between adjacent nuclei in a crystal of that element. For elements that occur as molecules such as O2, N2, H2, atomic radius is half the distance between nuclei of identical atoms that are chemically bonded together. Trends within a group, so remember, group and a family are the same thing. Atomic radius generally increases as you move down a family or group because, number one, you are increasing the number of energy levels, so the increasing main energy levels. So as you go down, for instance, lithium has 2 energy levels, sodium has 3, potassium has 4, rubidium has 5. The more energy levels you have, the electrons are further from the nucleus, so it offsets the pull of the increasing nuclear charge. Plus the fact going down a family or group, you have something called shielding. So you have the shielding effect. With each additional main energy level, additional orbitals between the nucleus and the outer electron are occupied, thus shielding the outer electron from the pull of the nucleus. So if you were talking about potassium's outer shell electron, then all of the electrons in the first, second, and third electron, and it would shield that outer electron from the pull of the nucleus. Trends within a period. In general, there's a gradual decrease in the atomic radii as you move from left to right across a period. This is because there is an increase in positive charges in the nucleus and the fact that the electrons are added to the same energy level as you move across the period. There is no shielding effect, so there's never shielding across a period, and the result is that the increasing nuclear charge, because you're adding, for each new element, you're adding one more proton, pulls the outermost electrons closer to the nucleus. For your transition metals, size changes little in the transition metals because the electrons are added, are core electrons. Okay, so we're going to write on our second arrow going down, we're going to say atomic radius increases. And going across on the second arrow, we're going to say atomic radius decreases. Okay, so if you'll put the video on pause for a second, you have a couple of examples. All right, the first problem says, which has a larger atomic radius, carbon, fluorine, beryllium, lithium? So we have carbon, fluorine, beryllium, lithium, so they're in the same period, and you want to know who has the largest, so you know that atomic radius decreases going across, so the largest would be lithium. The second question, who has the largest, that should say largest atomic radius, magnesium, silicon, sulfur, sodium. So sodium, sulfur, magnesium, and silicon. So once again, they're in the same period. So as you go across, they become smaller, so you should have circled sodium. And then which has the larger radius? Helium, xenon, argon. So these are your noble gases. So radius increases going down because you're adding energy levels, so it should be xenon. Okay, our next trend is ionic radius. So an atom that has lost or gained electrons is called an ion. So ions are atoms that have lost or gained electrons. There are two types of ions. You have cations and anions. A cation is positively charged because it has lost electrons. They're going to either lose 1, 2, or 3. They will always be smaller than the parent atom because the loss of an electron from an outer level may leave it completely empty, so it will have a smaller radius. In addition, the positive charge of the nucleus remains the same. And so, for instance, if you have lithium, or let's do sodium, if sodium lost an electron, it has 10 electrons but still has 11 protons. So if you have more protons, it's going to pull those electrons in closer. So the positive charge of the nucleus remains the same, so the electrons are pulled in closer. Anion are defined as negatively charged ions because they have gained 1, 2, or 3 electrons. They will always be larger in size than their parent because when you add electrons, it increases repulsion between the outer shell electrons, causing them to spread out. Okay, so trends within a family. So trends within a family, the ionic radius for both cations and anions increases as you go down. Within a period, going from left to right, there's a gradual decrease in the size of a cation. Then beginning with group 5A, which are your anions, they start out larger, but then they decrease from one anion to the next as you go across. Okay. So let's mark on our table. So our third arrow going down, we're going to say ionic radius increases. And going across, we're going to say, so we have two sets of arrows, and these represent your cations, so they're going to have a positive charge. So we're going to say cation radius decreases. And then starting at 5A, these are going to be your anions to 7A, so anions are negative. So then we're going to say anion radius decreases. Okay. And there should be a nice table in your book to look at. Okay, isoelectronic ions. We talked about them a little bit in the last chapter. These are a group of ions that will have the same number of electrons. The one with the highest atomic number is the smallest because more protons are pulling on the same number of electrons. So for instance, sodium, sodium plus, magnesium 2 plus, neon, fluorine minus, O2 minus, and N3 minus are all isoelectronic. They will all have 10 electrons because sodium had 11, it got rid of 1, so it's going to have 10. Magnesium had 12, it got rid of 2, so it's going to have 10. Oxygen had 8, it picked up 2, so it's a 2 minus, but now it has 10. Okay? They will all have 10 electrons. Of these, magnesium Mg2 plus is the smallest because it has 12 protons pulling on 10 electrons, and so the greater the proton number is compared to the electron, the more it pulls it in tighter. N3 minus is the largest because it has 7 protons and 10 electrons, and so the electrons win the tug of war, plus the fact that you have 3 extra electrons in that outer shell and they are getting away from each other as much as possible. Okay, our next trend is ionization energy, or IE. It is defined as the minimum, so you're going to have to write a lot right here. It's the minimum energy required to remove the highest energy electron from a gaseous atom to form a positive ion. is the minimum energy required to remove the highest energy electron from a gaseous atom to form a positive ion. A general formula, we just chose lithium as an example. Lithium in the gaseous state plus energy. So when you move an electron, it becomes an Li plus the electron is released. Think of ionization energy as how tightly electrons are bound to atoms. If they have a high ionization energy, it indicates the atom has a strong hold on its electrons and are not likely to lose them to form a positive ion. If they have a low ionization energy, it indicates an atom loses its outer electrons easily to form a positive ion. Now, we have several different types of ionization energy, first, second, and third. First ionization energy is the energy needed to remove the first electron. Second ionization energy is sometimes written as IE sub 2, is the energy needed to remove the second electron, but it's being removed from somebody that already has a positive charge, so from a positive ion. It will always be higher than the first ionization energy because now you have fewer electrons and the protons are pulling on them tighter. Third ionization energy, or IE3, is the energy needed to remove the third electron from a 2+ ion, so it's already gotten rid of 2. The energy required for each successive ionization always increases, however, not by equal amounts. For each element, there is an ionization for which the energy jumps dramatically, which shows an atom holds onto their inner core electrons more strongly than their valence. Okay, so you've got this table, I think, on your notes, and it's going to be in the notes in a second, but we're going to talk about it. So, for instance, lithium, sodium, and potassium are all 1A. Now, if you look at their first ionization energy, you notice lithium's is 520, sodium's is 495, and potassium's is 418. So there's a general decrease in first ionization energy as you go down a family. This is because these sodium's outermost electron is further from the nucleus than lithium's, and so it's easier to remove. Now, here's what we want to look at. All of these, sodium, lithium, and potassium, all have one valence electron. So for lithium, it takes 520 kilojoules per mole to remove that first electron. If you want to remove its second electron, look at the jump. It is 7,200. The reason it's such a big jump is it only has one outer shell electron. If you want to remove the second, it is from the next shell in that is full. Okay? The same for sodium. To remove its first electron is 495 kilojoules, and then it jumps to 4,500 because that next shell in is full. If you're looking at beryllium, magnesium, and calcium, those are your 2A. They have two outer shell electrons, so for beryllium, it takes 900 kcals for the first electron, and then 1,700. It takes a little bit more for the second electron because it's held a little bit tighter. But if you want to remove the third, it jumps to 14 because the third electron for it would be an inner shell. The same for magnesium. It takes 700 and something for the first, 1,400 for the second, and then your big jump is between the second and third. So you're going to find that for 1A, the jump is after the first electron. For 2A, it's after the second electron. And then for 3A, it would be after the third electron because you're moving then to an inner shell that is full. For the group 1A metals, hydrogen, lithium, sodium, for example, there's a large increase in energy between the first and second ionization energy. It is easy to remove the first electron from this group because the outer sublevel contains only one electron, but it's very difficult to remove additional electrons. So for sodium, the first energy level is fairly low, but the second energy is very high. For group 2A, the large increase in ionization energy occurs after the second electron is removed. And then for group 3A, the large increase would occur after the third electron is removed. Okay, so trends for ionization energy for a group, and these are for the representative elements, your 1A, 2A, and then 3A through 8A. First ionization energy generally decreases as you move down a group. because the valence electrons are further from the nucleus and are held less tightly. Within a period for the representative elements, across a period there is a general increase in the first ionization energy as you move. The atomic size decreases and valence electrons are held more tightly. So in general, you can say nonmetals will always have a higher ionization energy than metals. Okay, so on our table, we're going to go to the third arrow going down, and we're going to say first ionization energy decreases. So we've had three that have increased: metallic properties, atomic radius, and ionic radius. Ionization energy is going to decrease. And so going across, we're going to say first ionization energy increases. Okay, so you have a couple of problems. All right, so who has a higher ionization energy, sodium or potassium? Well, if ionization energy decreases as you go down, sodium would have the higher. Okay. As you go across magnesium and to phosphorus, ionization energy increases, so phosphorus should have the higher. Next is something called electron affinity. Electron affinity is defined as the energy changes that occur when an electron is added to a gaseous atom. It is usually exothermic. So when you look at this table, notice that these are negative values. Negative simply means that energy was released. An example would be nitrogen in the gaseous state plus an electron. So it's picking up electrons, so it becomes an N minus plus energy was released. All right. Trends within a group. As you move down a group, it's harder to add electrons. Okay. And then, so they're going to release less energy. And then within a period, as you move across a period, the electron affinity increases with the halogens picking up electrons readily. But there are many exceptions to this rule. Okay. Now, what I'm going to do is, because I look at this different than most people, so I'm going to let you choose what you write on this arrow going down and the arrow going across for affinity. Keeping in mind that the negative value means that that energy was released. Okay, our last trend is something called electronegativity. And you should have in your possession a periodic table that also has some polyatomic ions on the back and another table at the top. And this one's not very easy to read, but for instance, below hydrogen you see 2.1, and then below fluorine 4.0. So for these values, the values that are written below the symbol, those are your EN values. Okay, so electronegativity is how strongly one atom attracts the electrons of another atom when a compound is formed. Linus Pauling developed a system where the EN values are expressed in terms of numerical values of 4.0 or less. And so one way you can remember where the higher ones are is remember FONCO, phone call. Fluorine, oxygen, nitrogen, and chlorine have higher values. In a chemical bond, so we'll come back and talk about this in the chapter where we do bonding, the atom with the greater EN value will more strongly attract the bond's electrons. Group trends. Within a group, so if you're looking at your table, you notice that the EN values decrease or they have similar values as you go down. And this is because larger, more easily ionized atoms attract electrons less stronger than smaller, less easily ionized atoms. Your alkali metals, which are your 1A, and your alkaline earth metals, which are your 2A, are the least electronegative. They have very little attraction for electrons in a compound. They often lose electrons to form cations. So they're not wanting electrons, they're going to want to get rid of them. Nitrogen, oxygen, and the halogens, so N, O, and the halogens are the most electronegative. When you put them with a metal, they're going to gain electrons to form anions. Okay, your periodic trends. Across the period, there's a gradual increase in EN. Your nonmetals are generally more electronegative than your metals. The lowest ENs are found in the lower left side of the table, cesium having the lowest EN, while the highest EN values are found in the upper right, with fluorine having the highest. So with EN values, not only is there a trend going down a family where it decreases and where it increases going across a period, there's a diagonal trend where it increases diagonally. The noble gases, if you'll look at your table, are not typically, at least the top ones, are not assigned values because they have an octet of electrons. Now, some of your, like krypton and xenon and radon, can actually form bonds, and they do, but the top ones are not assigned a value. So, which of the following has a greater EN? Sodium or rubidium? So you find the location on the table. So you have sodium, you have rubidium, so your EN values decrease as you go down, so the greatest EN should be sodium. Sodium or rubidium, oh, I just did sodium or rubidium, I'm sorry. Oxygen or fluorine, well, fluorine's the most electronegative, so you're going to circle it. And then cesium or sulfur, well, it's diagonally, it increases, so sulfur would have the highest. For metals, as a general rule, as you move down the family, they become more metallic. We mentioned that on the last video in nature, and they become more reactive. So metallic, in my mind, just means that it's not that they're more shiny, it's that they give up their outer electron easier. Group 1A are the most reactive, with cesium being more reactive than K, potassium. They want to give up that outer electron. Group 2A are not quite as reactive as 1A. Metals will often lose electrons, remember, to form cations. So keep in mind that 1A always gets rid of 1, 2A 2, part of these in 3A 3. So they become 3 plus 2 plus or 1 minus cations. The most reactive nonmetals are located at the top of 7A. The most reactive nonmetals are located at the top of 7A. Nonmetals tend to gain electrons to form anions. Nonmetals tend to gain electrons to form anions. So if I'm not mistaken, this is not on your notes, so you need to add this to your notes. All right, so that finishes up for chapter 6, and now you will complete set 2. All right, let's go ahead on our table. I'm sorry. Let's go ahead on our table. So you should have written something for the this arrow going down for EA, and so we're going to say EN, which stands for electronegativity. EN values decrease. And on the last arrow going across, we're going to say EN values increase. All right, thank you.